For nearly 2 decades, Language Integrated Query, or LINQ, allowed developers to interact with data using clean, strongly typed C#, instead of opaque SQL strings. We moved from a tangled mess of raw database commands into organized, compile-time-checked code. But that abstraction carried a hidden tax. Translating those elegant statements at runtime meant dealing with heap allocations from closures, a heavy reliance on reflection, and naive SQL translations that drag down application throughput. .NET 10 re-engineers this execution pipeline. It targets these historical bottlenecks by analyzing expressions at compile time and leveraging modern CPU instructions, all while preserving the exact declarative syntax you already use. This focus on the internal pipeline allows the .NET 10 runtime to apply optimizations to existing codebases, targeting hardware-level bottlenecks that were once inseparable from the LINQ abstraction. To understand how these optimizations function, we have to split the LINQ pipeline into 2 independent execution tracks. This C# expression tree bifurcates into 2 paths. First, the local IEnumerable track uses low-level CPU architecture. Second, the remote iQueryable track translates C# nodes into optimized SQL. Across both, reflection is removed, guaranteeing trim-safe compatibility for native ahead-of-time compilation. Decoupling these models allows .NET 10 to apply optimizations tailored to the specific constraints of the target environment, whether that is a local CPU register or a remote relational engine. Let's look exactly at what happens on that local enumerable track. Historically, methods like where and distinct relied on a sequential iteration model, pulling and checking one element at a time from a collection. Instead of a sequential scanner checking a single data block, .NET 10 introduces the vectorized equality comparer. It drops a single instruction bracket to process 4 blocks simultaneously. Leveraging AVX512 hardware instructions, the runtime forces the CPU to evaluate multiple primitive types in parallel. Operations like sequence equal, min, and max now bypass sequential loops entirely and drop straight into this vectorized approach. By running these methods on .NET 10, primitive type evaluations see up to a 4x speedup purely from this hardware vectorization. The C# abstraction is no longer a high-level compromise. Your standard LINQ queries compile directly into optimal machine instructions. Processing speed is only half the execution equation. The other major local bottleneck is memory allocation and the resulting garbage collection pauses. Complex queries using aggregate or where historically struggled with boxing, taking lightweight value types and wrapping them in object allocations on the heap just to pass them through a delegate. .NET 10 rewrites these internal state machines. It utilizes ref returns and by ref closures to pass data directly, eliminating the need to box value types. Comparing the volatile memory heap to the stack, watch how data bypasses the heap entirely. It routes straight into a tightly packed stack block, utilizing the new span overloads. Methods like reverse automatically detect these span-backed arrays, performing in-place inversion without generating new objects. In high-throughput back-end microservices, establishing these zero-allocation execution paths reduces heap pressure and cuts down the unpredictable latency spikes caused by garbage collection. Now we hit the remote iQueryable track. Every link to entities query must leave the local environment and fire across the network to a database server. The core challenge here is translating the C# abstract syntax tree into sargeable SQL that can effectively utilize database indexes. Before EF Core attempts to write SQL, a new SQL expression normalizer passes over the unoptimized expression tree, collapsing redundant nodes into a clean structure. Simultaneously, the iQuery expression interceptor lets developers inject custom optimization rules directly into the tree, modifying the query before conversion. The combination of normalization and interception allows EF Core to actively reshape query logic during the pre-compilation phase, ensuring the database receives only the most efficient expression structure. We can see this engine at work on the most common database bottleneck, offset pagination using skip and take. Traditional skip commands force the database to count and scan through every single bypassed row, degrading performance as tables grow to millions of records. When the compiler detects a skip of 50,000, the resulting SQL morphs into a highly optimized keyset pagination query, seeking directly to the relevant ID. Furthermore, complex select transformations are now frozen into cached blocks, bypassing query plan generation entirely on subsequent runs. By evaluating complex filtering and pagination logic natively on the database server, EF Core eliminates the primary causes of slow queries and client-side evaluation warnings. Despite these engine improvements, there is a persistent misconception that complex data relationships require writing raw SQL or convoluted LINQ workarounds. Left, a legacy LeftJoin workaround, combining GroupJoin, SelectMany, and default of empty. Right, the new .NET 10 single-line LeftJoin method, both output identical SQL. LeftJoin and RightJoin are now native, first-class operators that guarantee clean, indexable SQL generation without the syntactic noise. The base class library also directly integrates system.link.async, bringing full async enumerable support to your queries without requiring external NuGet packages. The LINQ API surface has caught up to the operational reality of modern enterprise architecture. The need for custom extension libraries and hacky workarounds is gone. Here, we see data flowing from a database node through EF Core into local memory and out to the client. Notice optimizations triggering at every step: key set SQL, zero allocation spans, and SIMD vectorization. Because reflection is strictly removed, the application is fully native AOT compatible. Operationally, compiling ahead of time means the application deploys with a reduced memory footprint and executes with near-instant startup times, which is essential for serverless environments. You retain the highly readable, declarative C# syntax, while the runtime assumes the total burden of hardware-level optimization and precise SQL generation. Upgrading to .NET 10 ensures that the runtime handles the complexity of hardware-level optimization and SQL generation, allowing your core business logic to run with maximum efficiency without a single manual refactor.